Good afternoon, everyone. My name is Avery Johnson. I'm a junior mechanical engineering major from Chesapeake, Virginia. My other colleagues will now introduce themselves as well.
Hello, my name is Samuel Franco. I'm also a junior mechanical engineering major from Richmond, Virginia.
I'm Patrick Clark. I'm a mechanical engineering major from Sacramento, California.
Is Erie?
Well, our last member is Ray Maracchino. He's a junior mechanical engineering major as well.
Okay, so the objective of the overall presentation originally was that we had a shape optimization of a 2x2 cube with a maximum load bearing. The constraints was only 40% of the volume that was necessary for the design. So the maximum volume was about 3.2, less than 3.2 inches cubed. The goal was to get the highest safety factor possible based on that optimization, and the tops and the bottom of the structure should be covered in a 2x2 in the areas with the exception of reasonably sized fillets. The design had to have the availability to be manufactured using FMD 3D printing, as stated by Dr. Bay's original instructions. So the original thought that we were going based off of was that off the parameters, we decided to have a shape optimization with varying internal structures to see what produced the highest safety factor. The parameters that we gave for ourselves as a group was that we applied 1,000 pound force on the top surface. The material that we used was steel, and we had an absolute mesh size of 0.05 inches. Each group member was required to make their own optimization. We had to compare it amongst each other to figure out which one was going to be the best one to be used. And then we try to incorporate lattice structures to the best design to see if we could reduce the volume and thus add more support. So the initial design, one of the first designs was where we only preserved the top and the bottom of the plates. This provided us a 40% shape optimization, and it returned a very uneven type of angles as well as support as shown by the diagram. You can kind of see how the legs were of varying sizes. There wasn't a specific thickness to it. But at the end of the day, it did produce like 4 rectangular pillars on the corners of the structures, which led to the design as a whole. However, because of the odd shape, it ended up creating a very odd structure. Fillets were added as a result. The fillets were added to supports that touch the tops and the bottom of the plate. This provided us a minimum safety factor of 3.547, reminding again that this was us using steel originally. However, we did have a volume that went over the requirement. This was probably due to the fact that we had too much thickness in the legs, because we couldn't specify how large the actual leg size was. And there was also overhang in between the supports, which would have caused difficulty for us to when it came to printing. The top plate was the weakest due to the small thickness and space in between the supports. As you can kind of see by the diagram, because of how close the legs were, the only place that the table actually had to divot into was that small little gap. So that's why you see that large displacement right there when the load was being applied onto it.
All right, so for our second design, since we had issues with the legs in the first one, we preserved not only the top and bottom region, but also the cylindrical supports to get more consistency with the shape. We preserved 4 cylindrical regions evenly spaced on the corners of the cube. And when we ran our optimization, came out pretty evenly, but with more volume towards the top of the structure, since that's where the load was. And when we promoted this design, we followed the mesh as closely as possible to make sure that we got the optimum results from our adjustments.
So So as you can see here, this was our result for the previous preserved regions, and this model was symmetrical all around. The top and the bottom were the same. If you cut a plane any direction, it would be the same on both sides. Unfortunately, the volume very barely exceeded the allowable amount at 40.51%. And for this reason, we didn't test the safety factor edits to get it down so we would have something to go off of. And also, this was again before overhang was discussed, but there was slight overhang on the top corners where the arches kind of went towards the edges of the plates. And to make some more edits to this design to make it work, fillets were added on almost every single straight edge that was found. As you can see, this one looks a lot more rounded around the bases than the last design. After a preliminary test, the sizes of the arches where the pillars connected the top and bottom plates were also increased because these were determined to be the highest stress regions. And to meet that volume requirement, the volume of the bottom plate was decreased. As you can see, it's a little bit thinner than the one on the top plate because the stress results showed that this region had the highest safety factor and the lowest stress concentration. So we removed some volume there, and that allowed us to reach the volume of 37.8%, which was well within the margins, and a safety factor of 11.46, again, using steel. And but the arches along the top where the pillars connected the top plate still showed the highest stress concentration and lowest safety factor.
Okay, so I'm just going to introduce myself again. I'm Irolua Elijah Morakio, and I'm a junior mechanical engineering major from Ibadan, Nigeria. So we had two initial designs, as my team members have explained, but we kept like making iterations just to see which one's going to be the best fit. So we made this new design, and we just did optimizations to make it just one central support, but make sure it was a cylinder in the middle. And then first, we made the bottom and the top plates rectangular, and then we made some static stress tests just to make sure like it fit the required it fit the required methods we're supposed to use. And then so we could reach the size of the central support, we made sure that we made the corners angled and the fillets were added just to make sure we spread up the stress concentration. And then we made the top plate thicker than the bottom by 30%. And then we made initial fillets for the support so that it could fit, it could spread out the load distribution. Then after we made a couple tests, we found out that the safety factor was 4.523. But then by this time, we were still allowed to use any material we wanted. So we used steel, and then we found out that the minimum safety factor was 4.523. And as you can see in the diagram, we can see the highest stress points, and it's kind of like around the area where we added fillets. And then it was also where the support touched the plates. And then also based on the design models we're given, the volume was also 39.44%, which kind of fit in the middle of what was asked of us to do. And then but the only problem with this, or one of the problems that was with this design, was that it had a very large overhang, as you can see. And given the situation we are right now, the 3D printer could not print this because of the overhang. So we had to think of more designs to use that could fit the model.
Okay, so for our fourth design, we kind of took an opposite approach from the third one. We incorporated 6 smaller pillars to see if that would improve support. We made an initial simulation on the stress, and like with the others, we reduced the volume of the bottom plate because stress was concentrated at the top where the load was applied. Wasn't much need for the mass at the bottom. And then we added fillets both at the bottom and the top. Stress concentration because that's where most of it was occurring.
Oh, sorry. Oh no. Whoops, my bad. There we go.
Okay. Yeah, this one, as with others, we initially ran a steel simulation and we came out with a minimum safety factor of 7.725. High stress areas at the top where the supports were touching the plates, just as with the previous designs. Definitely volume was within 40%. We got it down to 34.38%. We did have quite a bit of overhang, but we adjusted that in later designs after Dr. Bay told us that this wouldn't be acceptable for 3D printing.
So we had done a couple changes in the objective. After there was a discussion, Dr. Bay told us that he tried printing our first trials, and he just needed to make some adjustments. So then the first thing he said was to make sure the material we used in the testing was ABS plastic, just because the printer was only going to be able to print with the ABS plastic, and using steel wasn't, realistic. And so him saying that just changed everybody's design, and then we have to go back to the drawing board. We have to go back to square one, and then think about new ideas and to make sure we can use ABS plastic and still increase the safety factor. And then we submitted design 2 for trial submission, but it had a safety factor of 11.46 with steel. But then we changed the material. After changing the material to ABS plastic, it had a safety factor of 1.135, which was a lot lesser than steel. And we tried using NetFab to help us hone in on our design and to get the latest structures, but we didn't have an account or we couldn't get in, so we had to leave that part of the design. And then we just came together again, and then we made individual designs, and then we just decided to come together and then test it, and whichever one met the requirements was going to be sent in.
So for our final design, we decided to go with a honeycomb pattern because Dr. Bay in class always talked about how this is supposedly a really strong structure. So we thought we'd give it a shot. And initially, the way we created the shape, we just made a outside border, which was a square shape. And in the center, we placed a hexagon and used the rectangular pattern tool to extend those hexagons in every direction. And we didn't really do too much else to it apart from some small fillets that can be seen on the edges. And after using the static stress simulation with the new updated, requirements with the 1,000 pound force, absolute mesh size of 0.05 inches, and this time with ABS plastic as the material, the stress concentration showed that the weakest points were at the very corners on the bottom, like pretty much just points.
I think you need to wrap it up. It's almost the time.
All right, well, I'm gonna go fast then. So for the update parts, we added a plate. As you can see, it doesn't cover the whole bottom, but just some of it. We hope that this would distribute the stress a bit more to get the highest concentration away from the corners. This improved it slightly from like 1.1 something to 1.207. The volume was exactly 3.2 cubic inches, so 40%. But we decided we wanted to make a few more additions, and that will be in our final part on the next slide. And for this, we decided to remove the fillets on the bottom altogether. The bottom plate was made thinner, so it didn't protrude as much into the center, but it was made taller. It's kind of hard to see in the image, but it was a little taller. And this actually greatly improved our safety factor all the way to 2.032, which was by far the highest out of all the trials we had. The volume was within the 40% at 39.775, and there was absolutely no overhang in this design, so it could have been easily printed. And here you see the printed results, the top view on the left, the bottom view in the middle. You can see the borders are a little bit thicker due to that plate, and then another top view on the right just from a different angle.
Well, it was just some real quick takeaways that we took from it was overall that we understood that honeycomb structure was the most optimum use for our structures, or just circular structures in general. It apparently allowed us to have a higher safety factor. And we realized that it took a lot of trial and error just to get the results that we needed. So just looking over those things, we ended up getting the results that we got.
Thank you.
Sorry, presentation.
Yeah. So do you have any question from the audience or students first, maybe?
Yes. I have a question.
Okay, Brandon. Yeah.
The first group, they were trying to do the same, similar structure with a honeycomb. However, they weren't able to do it. What advice can you give to them in creating yours, like the one that worked for you?
The only thing that we did to try to make our honeycomb was using the rectangular pattern tool. I don't know what they tried to do, so I can't really speak on that part, but for us, we had no issues using that. We got it like within a few minutes.
Okay, thank you.
I have a question. You did a lot of design work up front. It actually looked like you guys put in quite a bit of work, and then just kind of pivoted last second. If you'd had more time, would you have tried to apply the honeycomb to your initial design?
That could have been a thing we had to do. However, since the honeycomb does take a lot of internal volume out, I feel like we would have had to done at least a good bit of remodeling, even to like the trial 2 design or 3, just to have that added volume that have been taken out from the honeycomb parts, removing that.
Yeah, about Brandon's question. Yeah, I don't know how the first group did, but it seems like based on the model, they had elements like shell elements, like a honeycomb shape, and then they repeat it. So maybe those elements might not be bonded or like unified together. Maybe they could cause some issues.
Yeah, for us, we did the structure first before we extruded anything. So we just drew the honeycomb design on like a 2D surface,
Right.
and
So
then extruded out.
in this case, they have like a one single body, so they don't have any issue with that. Yeah.
I see.
Yeah, for our team, it had like over 100 bodies, but the issue was when we tried to combine them, that was when Fusion kept crashing. So we were never able to combine and run the study.
Okay. Okay. Yeah. So that's like a bottom up design, and this team they do like from the bulk, and then they took away volumes.
So just a quick question is that Dr. Tyagi from UDC. So if so, it's a kind of conceptual question. If some of the honeycombs they are supposed to be kind of further reinforced, then what kind of approach can you visualize?
Well, if we had to reinforce the honeycombs, we could just increase the distance between the pattern, which would have increased the thickness of the webbing in between. However, from our results, the honeycombs themselves were not the weakest part of the structure. It was still the bottom 4 corners, which didn't have like any shape, or it was just the corners. I guess there was no honeycomb in those areas.
Okay, very good. Thank you. Yeah, good work.
Thank you.
Thank you.